Hi, my name is Francesco Volpe. I'm the founder of Renaissance Fusion, a startup located in Grenoble, France, and in Villingen, Switzerland, which employs 60 people from 17 different nationalities and has a global vision. Our two-pronged global vision is, on the one hand, to put heat and electricity from fusion on the grid in the early 2030s, and on the other, in the shorter term, to develop superconducting magnets, which are essential for fusion, and we will also commercialize in pre-fusion markets. Fusion takes place in stars, and we are indeed building a star on Earth in a device called the Stellarator. Our star, our plasma, is a donut shape, in fact a complicated donut shape, but this complicated shape is essential, in fact is the only one, to generate fusion electricity continuously and therefore at the lowest possible price. The physics of this shape is complicated. The physics of the magnetic field is complicated. Now, how to generate that, by which engineering, that can be simplified. A traditional method is to wind copper or superconducting tapes around the plasma, following the same complicated shape in complex three-dimensional sculptures. This is obviously very complicated, so we decided to replace this sculpture process with a painting process in which we coat large cylindrical surfaces with superconducting material. Effectively, we make a canvas of superconductor, and then we paint it by means of a brush, a laser brush. And the result is a cylinder, superconducting cylindrical printed circuit, where the current is guided by these patterns in these zigzag routes in such a way that it generates the complex field necessary to confine the plasma. Now, this technology, which we have already demonstrated as far as the engraving is concerned, and we are in the process of depositing our own high-temperature superconductor over large surfaces, has a number of applications outside of fusion. You can imagine, for instance, a large cylinder pattern to make medical imaging, or a cylinder pattern to make a component for a particle accelerator for cancer therapy, or for energy storage. These are, in fact, the first applications in which we will start commercializing our technology as early as 2025. Now, in the Stellarator, you have these strong magnetic fields generated by these HTS deposited and patterned on the outside of the cylinders. We are making very compact plasmas, and we, as well as all other tokamak and Stellarator startups, are going for Q greater than 1. So more heat out of the plasma than heat in the plasma. It's a lot of heat, and it's a lot of neutrons, and there is a tendency to go to smaller and smaller, and therefore more affordable devices. But no other fusion startup has looked at how to cope with this intense heat flux and neutron flux. Renaissance Fusion is the only startup that deals with this problem. How? By levitating a layer of liquid metal all around the plasma. Imagine this layer of liquid metal hanging from the ceiling, the walls, and the floor, flowing, so it copes with the heat. In fact, it extracts the heat, and it is thick enough to stop the neutrons and preventing activation of the device. In this experiment on my back, Skyfall 1A, we inject liquid metal from the top, and rather than just letting it fall by gravity, we apply electromagnetic forces by means of magnets and electrodes, and these electromagnetic forces push radially outward so that the liquid metal flows along the walls of the cylinder. This has been demonstrated for now with a layer of thickness 10 cm with a dense material, equivalent in the lighter fusion-relevant lithium-lithium hydride material to this thickness, 120 cm, which is well beyond our needs, 35 centimeters in the fusion-relevant material. So check the aspect of levitation has been demonstrated, as well as the minimization of droplets splashing from the liquid metal into what will be the plasma. Not that this is a major issue, but droplets can interrupt the plasma discharge and force us to restart one. And of course, excessively frequent interruptions are undesirable in a power plant. So this was also addressed in these devices. Next, we will explore materials of higher temperature and closer to the composition needed for the fusion reactor. And the combination of this liquid metal technology and this superconductor technology will be combined, the two technologies will be combined, and they will reach their pinnacle in a demonstrator, a cylindrical demonstrator, with HTS on the outside, liquid metal on the inside. No plasma yet, but this will be the module by which you can build a stellarator. If you can build one of these cylinders, you can build many and make a donut and make plasmas. This is it for now. Thank you from Renaissance Fusion. And here at the bottom you can see our coordinates. Visit our webpage, shoot us an email, let's talk about how to make fusion and superconductors together.